So here we are in section 4.3, talking about the diagnostics of the least square regression line. Um, and we're going to be using the linear correlation coefficient, if you recall, R, to compute R squared. Well, that's a simple case of just squaring R. And the information where we found it using the TI-84 will be the same place we find the the coefficient of determination. Okay, so before we get into computing it, what is really the coefficient of determination? It just measures the proportion of total variation in the response variable, recall that's the y-axis, that is explained by the least square regression line from your data set. Now, because you're squaring a number, now we know r was from -1 to 1 in between, we're going to get a positive number. That is why r squared is only between 0 and 1. If it's 0, the line has no explanatory value, and if it's 1, it explains 100% of the variation in the response variable. So the predicted versus the actual. You can take the time to look at these examples, stop it at your discretion, and go forward from there. I'm just going to kind of skip through until we can see how the computation works out and how clearly you don't need to do that because of the enhancements of these calculators. So you can kind of scroll through, get what you need from these examples, and go back up. Now the difference between the observed and of the response and the mean value is called the total deviation, and we'll be using that to find r squared, but that's all going behind the scenes of the calculator. So all this, what I'm scrolling through, is part of the total formula. However, let's take the time right now to actually compute it via the calculator. So the first thing is, if you recall, make sure you go second catalog, make sure your diagnostic is on. You can just hit the D right here by the make the inverse. Scroll down to diagnostic on. And there we are, diagnostic on. I press enter, we're done. So I know once I have my data set, it's going to compute R and R squared. So stat, right? Edit. Now I already have information from possibly other classes in here, and I'll just use any of them. It may not even be a good linear fit, but I just want to show you how this will compute out R and R squared. So let's take, I don't know, L3 and L4, a small sample set here. Once again, stat. Let's calculate some regression line, and this particular unit is linear regression. Now, in other classes, you'll be using quadratic, cubic, quartic, and so forth, but for us, we'll look at linear regression. And I have my stats in L3 and L4. You might have it in L1 and L2, whatever you need. I'm going to kind of enter through the data, and here we are. Notice our regression line, right? We have our slope, we have our y-intercept, and now we have down here, as if you recall, is our linear coefficient, and it happens to be negative. But when I square that number, r squared, it becomes positive, and it's 0.89 and so forth. So that is the coefficient of determination, r squared. It talks about the variance. And that's basically it. So if they're asking for r squared, you can just go ahead and transfer it from here. Just make sure we're rounding off to the correct decimal place. As we scroll on into this 4.3, we have other examples that you can take the time and see how they compute it. And clearly, if you look up here, our decimal was 0.89, right? Their decimal was 0.59, but turning that into percent by multiplying by 100, it's about 90%. So for our example, whatever data I chose, it was about 90% of the variability in drilling time is explained by the least squares regression line. For this example, it's almost 60%. Some more examples. Okay, so These play an important role in determining the adequacy of the linear model. In fact, residuals can be used for the following purposes. To determine whether a linear model is appropriate to describe the relationship between the predictor and the response variables. You come back over here and you press Stat. For this particular course, we've been dealing with number 4. But if you look below 4, we have quadratic, cubic, quartic, and so forth. When you get to other classes, whether it's in high school, if you choose to pursue your school in college, you might be taking a college algebra class that uses other regression lines. But for us, we'll stick with the linear. Now, it also uses to determine whether the variance of the residuals is constant. And to check for outliers. Outliers really is something that doesn't really conform to the rest of the data set. Let's just say you took 15 tests in one of your classes and you received a B on about 14 of them. And then just one day you woke up with a headache, I don't know, got into some issues before school, you weren't feeling great, things were getting you down, and you get a D. Well, that D would be an outlier. It just doesn't fit the norm of the rest of the data set. The plot. This would be appropriate linear model. You have values that are above the mean. You have values that are below the mean. Well, look at this residual plot. It follows a pattern, almost a U-shaped pattern. This linear model would not be appropriate because it follows a U-shaped pattern. More examples that you can read through. Residuals, once again, not appropriate because it follows a pattern. This word of homoscedasticity, not used that very often. It may just come up on a vocabulary quiz in probability stats. The constant error invariance, that's really what it talks about. It's just something that comes up, not necessarily going to make or break what you know about this class. And like I said, just take your time, go through some of these examples, see what they're asking, and apply it to any of the questions you have on the quiz or the applying the concepts. So if you look at the data, this example draws a residual plot of the drilling time from the previous data set. And you can see clearly this would be a good linear model. Now, an influential observation and one that has a disappropriate or proportionate effect on the value of the slope and y-intercept in the least squares regression equation. So, like I said, if you're computing grades and every grade is an 80, 81, 83, 81, 82, and then you pull a 58, well, that clearly is going to have a pretty strong effect on the least squares regression line. And you can see in case 2 and 3, they're just out of nowhere. And more examples. And this is from different statistical software, so don't worry about what this actually is. And you can read this about outliers. And that's basically 4.3. It's really the focus is the coefficient of determination, but with the use of the graphing calculator, not so much of an issue.